Hi, welcome back to the series of lectures on major theory with course code MMTC 202. Today, in this lecture, we will discuss Ostroviskis theorem. Ostroviskis theorem. Ostroviskis theorem, which states that let f be a function from R to R, function from R to R, be additive. Suppose this function is additive. This function is additive. Additive means that that is f of x plus y is equal to fx plus fy. For all x comma y belongs to for all x comma y belongs to R, and Lebesgue measurable, and it's also Lebesgue measurable, and Lebesgue measurable. And Lebesgue measurable. So that then f is continuous, then f is continuous, and hence of the type, and hence there exists C, and hence if it is continuous, and hence there exists a constant C such that fx is equal to C times x for all x belongs to R. That's a statement of Ostroviskis theorem. It is actually gives the measurable solutions of this function f from R to R, satisfying this equation fx plus y equal to fx plus fy. So the statement is f is a function from R to R, which is additive. That's additive means f of x plus y is equal to f of x plus f of y for all x, y in R, and it's also Lebesgue measurable. Then this f is continuous, and if it's continuous, then we already done every continuous function which is also additive is of this type. That means there exists a constant C such that fx is equal to Cx. So to prove this theorem, we make the use of following lemmas, which we have already proved. Okay. To prove this theorem, we make the use of following lemmas. The lemma number one. Lemma one is if f from R to R is additive and continuous at 0, if additive and continuous at 0, then there exists a constant C. There is a constant C such that fx is equal to C times x for all x belongs to R. That's already done actually, that lemma. This lemma number two, which is actually Ostroviskis, which is actually Steenhouse theorem. So let E be a subset of R such that its Lebesgue measure is positive. We have done Steenhouse theorem for Rn, but here we use the Steenhouse theorem for of R. Okay, such that its Lebesgue measure is positive, then there exists delta positive such that minus delta plus delta is subset of E minus E. We use these two lemmas to prove our theorem, Ostroviskis theorem. Proof. First, we show that f is continuous at 0. Then by this lemma 1, there exists a constant c such that fx, such that f of x is equal to c times x. And we also see that if it is continuous at 0, then it's continuous at every point because of the additive nature of the function f. And we also use this lemma to derive that, to show that this our function f is actually first we are making the use of lemma 2, then we use the lemma 1. So let's write the proof of the theorem. Okay. First, we assume that this f is non-zero, because if it is 0, then there is nothing to prove. So assume that f is non-zero function. Assume that f is a non-zero function, otherwise nothing to prove. Otherwise, nothing to prove. Okay, it's a non-zero function. Now, since now we verify that, now we verify that this n times f inverse 0 to epsilon n times f inverse the closed interval 0 epsilon is equal to f inverse 0 to n into epsilon, and we also verify this, and minus n times f inverse epsilon to 0 is, sorry, it's 0 to epsilon, not epsilon to 0. It's 0 to epsilon is equal to f inverse minus n epsilon to 0. Okay. So we verify first one only. So let's take this. Let x belongs to n times f inverse 0 to epsilon. Okay. This is true if and only if x divided by n belongs to f inverse 0 to epsilon. And this is true if and only if f of x by n belongs to 0 to epsilon. And this is true if and because f is additive function, so it means that 1 by n of this is already actually explained in already done in one of our lecture. This f of p by q times x is equal to p by q times f of x if f is additive function. Okay, so this belongs to 0 to epsilon, and this is true if and only if f of x belongs to n times this interval 0 to epsilon, which is true if and only if f of x belongs to 0 to epsilon, and which is true if and only if x belongs to f inverse 0 to n epsilon. So thus x belongs to n times f inverse 0 epsilon if and only if x belongs to f inverse 0 to n epsilon. So therefore n times f inverse 0 to epsilon is equal to f inverse 0 to n epsilon. Similarly, minus n times f inverse 0 to epsilon is equal to f inverse minus n epsilon to 0. Minus n epsilon to 0. Okay, so this is now verified. So now next we verify that. Next we verify that that this this epsilon is positive number. Okay, this is actually to choose this epsilon as positive number. So to prove this theorem, we use the following lemmas. Then suppose f is not equal to 0, otherwise it's trivial, and epsilon is a positive number. Okay, this epsilon is a positive number, and epsilon is a positive number. Epsilon is a fixed positive number. It's a given positive number. It may be it's actually any positive number, but in this process we fix it in the process of this theorem. So it's some fixed positive number. Next, we verified that the Lebesgue measure of this f inverse 0 to epsilon is positive. Lebesgue measure of f inverse 0 to epsilon is positive. That's very important, actually. So from this we can use this Steinhaus theorem, because the Lebesgue measure of the set is positive, then the set difference must contain some interval, actually. Okay, that's what we're going to use here. It's Lebesgue measure of 0 to epsilon is positive. 0 to epsilon is always a positive number. Its Lebesgue measure is positive. So Lebesgue measure of this interval is positive. Interval is positive, and we show that because Lebesgue measure of interval is epsilon, we show that the Lebesgue measure of the image is always also a positive number. This is not true in general. If Lebesgue measure of a set is positive, then it's not necessary that the Lebesgue measure of the image set is positive. But for this interval, it's true, and because this because of this, it's actually it's an interval, actually. Okay, so Lebesgue measure of the image of an interval is always positive. That's what I mean to say, actually. In general, it's not true. If the Lebesgue measure of the set is positive, then Lebesgue measure of the image need not be positive. That we'll discuss in the future. Okay, so we show that this Lebesgue measure is actually positive. So for if possible, it's 0. So it's either positive or 0, because it cannot be negative. For if possible, Lebesgue measure of f inverse 0 to epsilon is 0, which implies n times Lebesgue measure of f inverse 0 to epsilon is 0. It's suppose it is 0, then this is also 0, because its n times 0 number, and this one is also 0, and n times Lebesgue measure of f inverse 0 to epsilon is also 0. Okay, this is minus n times 0. So that implies this this Lebesgue measure of this because n times Lebesgue measure n times this is equal to n times Lebesgue measure is same as Lebesgue measure of okay, this is here actually it should be Lebesgue measure of n times because so I don't need to write this step. I don't need to write this one. Okay, it's not necessary here. Okay, so this implies Lebesgue measure of this of f inverse of 0 to n epsilon. This is 0 and it is same as Lebesgue measure of this one because it's equal to a constant times Lebesgue measure of a set is equal to Lebesgue measure of it's actually the property of the Lebesgue measure. So this is actually I have to first write it here. Okay, this is let me erase this, and here first it's actually n times this. Okay, and this is same as the Lebesgue measure of minus n times f inverse 0 to epsilon equal to 0. Lebesgue measure of f inverse of this is equal to f inverse of this. Okay, I will write this f here actually. I have to write this f here, not inside. It's here actually. Okay, it's here. So Lebesgue measure of n times of the set is equal to mod of n into Lebesgue measure of the set. Actually, we are using this property. Lebesgue measure of we are using this property. Lebesgue measure of a into a is a set is any real number. It's equal to mod of a into Lebesgue measure of the set. Okay, and here the set is our set is here f inverse 0 to epsilon, and that constant is n here. So it is n times actually Lebesgue measure of f inverse 0 to epsilon, which is equal to 0. Okay, because this one is n times is equal to 0, and here it's also n times because it's actually mod of n times. Here you can we have this formula actually Lebesgue measure of a into capital A is equal to mod of a into Lebesgue measure of the a. So this one will be this is our set A f inverse 0 to epsilon. So this is our constant. It will be mod of minus n times Lebesgue measure of f inverse 0 to epsilon, which is equal to n times Lebesgue measure of f inverse 0 to epsilon, which is equal to 0. So both are equal to 0. This implies Lebesgue measure of f inverse 0 to n epsilon, because n times this is equal to f inverse 0 to f. This is already done. This is same as Lebesgue measure of minus n epsilon in to 0 is equal to 0. So both are already done. Huh? Both here. You can see it here. N times f inverse 0 to epsilon is equal to f inverse n epsilon. And similarly, we have this minus n times f inverse 0 to epsilon is equal to f inverse minus n epsilon to 0. So therefore, this implies Lebesgue measure of it's Lebesgue measure here. Lebesgue measure of f inverse minus n epsilon to plus n epsilon, which is equal to Lebesgue measure of f inverse of this is a minus n epsilon to 0 union 0 to n epsilon. Okay, and this is equal to Lebesgue measure of this. It is f inverse this is here minus n epsilon to 0 union f inverse of 0 to n epsilon. So F inverse of A union B is equal to F inverse of A union F inverse of B. Okay, this one, it may be, I think it's subset. Subset or equal. You verify this whether this is subset or this F inverse of A union B, whether they are equal or sub. It's F inverse of A union F inverse of B are subset. I'm not sure whether they are equal or not, but subset is trivial. You can easily verify this. But that will not create any problem. I will write here this is less or equal to, okay? I will write this. Now it's the Lebesgue measure of the two sets. This is set A, this is set B. Lebesgue measure of A union B. It's less or equal to Lebesgue measure of A plus Lebesgue measure of B, which is less or equal to Lebesgue measure of F inverse minus n epsilon to 0 plus Lebesgue measure of F inverse 0 to n epsilon. But both are equal to 0, they are already done, so it's equal to 0 plus 0, that's equal to 0. So which means that Lebesgue measure of this set is 0. So this implies Lebesgue measure of, actually we show that Lebesgue measure of R is actually 0, which gives us the introduction. This is 0 for all n greater or equal to 1. Now what's Lebesgue measure of R? It's equal to Lebesgue measure of Lebesgue measure of these unions. You can see it's Lebesgue measure of the union is Lebesgue measure of R is equal to because this one it's equal to Lebesgue measure of it's because F inverse of R is R actually, so it's equal to Lebesgue measure of F inverse of R. Not a problem because F is a function from R to R, so that means F inverse of R is equal to whole R, which is equal to Lebesgue measure of F inverse union n runs from 1 to infinity minus n epsilon to plus n epsilon. So this union is whole R, and that's equal to it's like this F inverse of the union. So I will write in the next page. It's less or equal to, because F inverse of union is it's subset of the union of F inverses. So it's less or equal to Lebesgue measure of union n runs from 1 to infinity F inverse minus n epsilon to plus n epsilon. Okay. So this is it. And that's less or equal to, again using sub-additive property of Lebesgue measure, it's less or equal to summation n runs from 1 to infinity Lebesgue measure of F inverse of minus n epsilon to plus n epsilon. Okay, that's this, it's a Lebesgue measure, and which is equal to summation n runs from 1 to infinity Lebesgue measure of this one. What's the Lebesgue measure of F inverse minus n epsilon plus n epsilon for each n? It's equal to 0. So it's equal to 0 here. It is it's 0 here. It's 0. So that's equal to 0, because 0 plus 0 plus it's equal to 0. So this 0 plus 0 infinite times it's equal to 0, because it's by definition of series actually. So here the sequence of partial sums will be constant sequence with each term equal to 0, 0, 0, 0. So the limit of the sequence of partial sums will be equal to 0. So that's why this series is equal to 0. So thus this implies that Lebesgue measure of R is equal to 0 because it's less or equal to 0. So but it cannot be negative, it's equal to 0, which a contradiction. A contradiction because it is infinity actually. It is minus infinity to plus infinity, which equal to its length. That's equal to infinity. A contradiction. So therefore, our assumption that Lebesgue measure of f inverse 0 to epsilon is 0 is wrong. So that means it must be equal to non-zero. It's equal to some positive number. So therefore, we have this Lebesgue measure of f inverse. The set is 0 to epsilon. This Lebesgue measure of this set is positive. Is positive. So this is your set E. Now we apply the lemma 2. If the Lebesgue measure of the set is positive, then I can find delta positive such that minus delta to plus delta is contained in this difference of these two, algebraic difference of the set with itself. So by lemma 2, there is delta positive, or you can say by Stein's theorem, there is delta positive such that minus delta to plus delta is subset of f inverse 0 to epsilon minus f inverse 0 to epsilon. Okay, so it's subset of this. Minus delta to plus delta is subset of this set. Okay. So from this we show that it is actually continuous. From this we'll prove it's actually a continuous function. So and what it precisely gives actually. What it precisely gives actually. And this one you can see this one is equal to f inverse minus epsilon to plus epsilon. You can easily verify it. It's not too hard. This is minus epsilon to plus epsilon. So you verify it, okay? Using the additive property of f inverse 0 to epsilon minus f inverse 0 to epsilon is equal to f inverse minus epsilon to plus epsilon. Actually, this will be equal to f inverse 0 to epsilon plus f inverse minus epsilon to 0. And if you add these two using the additive nature of the function f, we'll see that this addition will be equal to f inverse minus epsilon to plus. That's very simple, that you can easily verify. So this one is subset of this. So which implies that this x lies between. Thus, that is this implies minus delta less than x less than delta. This implies minus delta less than delta. That's I will not write here implies. So this gives. Right, this gives this gives minus delta less than x less than delta. That means x belongs to this interval. If implies whenever x belongs to this, it implies that x should be here. X should be here means f of x lies between minus epsilon and plus epsilon. Okay, so this implies minus epsilon less or equal to fx and less or equal to epsilon, because whenever x belongs to minus delta to plus delta, it implies that x will also belong to f inverse minus epsilon plus epsilon, which gives fx belongs to the closed interval minus epsilon plus epsilon. That's this. So this means f is continuous. This means f is continuous at 0. So thus we can say for each epsilon positive I can find delta positive. Thus For all epsilon positive, there is a delta positive such that mod of x less than delta implies mod of fx less or equal to epsilon and you can replace this epsilon if you want strictly inequality. You can replace this epsilon by 2. Okay, or you choose first 2 epsilon, then you can write here less than epsilon by 2, which is less because it's less or equal to epsilon, therefore it's strictly less than epsilon by 2. Okay, so this means that this f is continuous at 0. Also f is additive. Also f is additive. Therefore this f is continuous at every point of r. F is continuous at this is also already explained in one of our theorem when we have proved the same result for continuous additive function. Okay, the lecture with the title continuous additive functions. So f is continuous at every point of r. F is continuous at every point of r. So f is continuous and additive. Now by lemma 1, whenever f is continuous and additive, you can see the lemma 1 here. You can see lemma 1 here. What's lemma 1? So actually you have to show that this f is continuous. Okay, so continuous. What's the statement of the theorem? That actually the proof of the theorem is complete. Actually, f is additive function and it's measurable. Then you have to show that this f is continuous, which we have proved, and hence there is a constant c, and this part follows from this lemma 2. Whenever f is continuous at 0, so by lemma 1, whenever f is continuous and additive, it's additive and continuous at 0, then we can find a constant c such that by lemma 1 you can see. So by lemma 1, there exists a constant c belongs to R such that f of x is equal to c times x for all x belongs to R. So this proves the theorem completely. Now we'll do an exercise which is very important. If G is a, now we'll use this application of Steinhaus theorem. If G is a subgroup of R, real line R, if G is a subgroup of real line R, under addition, under multiplication, it cannot be a group, so it is under addition actually. If G is a subgroup of R, so it's under plus sign. Okay, then show that the Lebesgue measure of G is equal to 0. Is equal to 0. This is the Lebesgue measure of G must be equal to 0. Okay. So here, if we can find a subgroup of G which is uncountable, and we find a subgroup of R which is uncountable, that subgroup of R is always a null set, because every subgroup of R is null set, proper subgroup. If G is a proper subgroup, you can see here it's a proper subgroup. If G is a proper subgroup, so any proper subgroup of R is a null set. So now the question arises, if it's a countable, it's always null set. If G is a countable and countable suppose G may be Q, the set of rational numbers, the big measure of that's always 0. But my question is, does there exist any uncountable subgroup of R? If it's true, then the Lebesgue measure of that set will be equal to 0. So that means there exists an uncountable subset of R having Lebesgue measure 0. So this is already our one of our this is already done for we don't have done it here, but Cantor constructed a set which is uncountable and having Lebesgue measure 0. That's called the Cantor set. But I want to use this approach actually. So I don't have seen it anywhere, but I think I can construct a subgroup of R which is uncountable, and that gives us the subset of R which is uncountable and a null set. Okay, so let me first prove this. It's a null set. Okay, solution. So assume Lebesgue measure of G is positive. Okay, by Steener's theorem or by lemma 2, there exists delta positive such that minus delta plus delta subset of G minus G, but G minus G is same as G because G is a subgroup of R. It's like when we have a multiplicative notation, H subgroup of G, then H into H is always equal to H. But here the operation is addition. So here instead of this product, we have this difference. Or you can say G minus G same as G plus G because minus G same as G. And this is equal to G, as G is a subgroup, as G is a subgroup of R. So that means minus delta plus delta is subset of G. So if it is subset of G, that it will give G is equal to R. So let's choose any element in R. Now let X belongs to R. Then there exists a natural number n greater or equal to 1 such that X belongs to this interval minus n2 plus n times delta. Okay, sorry, I will it is I can find such n always, is no problem. I can find such n always minus n delta to plus n delta. Okay, this X belongs to this set. This X, any real number, belongs to some interval actually. Belongs to some interval. Okay. And minus n delta plus n delta. But that will give X belongs to G because minus delta plus delta is subset of G and G is group under addition. So this X is in minus n delta plus n delta. Okay, and this is subset of G as minus delta plus delta subset of G. So how it is subset of G actually? This is using the additive nature, using that nature of because G is a group under addition. So whenever minus delta plus delta subset of G, then if you choose any element here, see, if you choose any element here, X belongs to say minus delta to plus delta, which is subset of G. Then 2x also belongs to G, 3x also belongs to G. Then this implies nx belongs to G. So here this is subset of G, okay? So x is in this interval, but where is nx? This nx is always subset of g because nx is equal to x plus x. But where this nx, x belongs to minus delta to plus delta, then nx belongs to minus n delta to plus n delta. So this is actually the point of this, and it also belongs to g. So that means this minus n delta plus n delta is subset of g. So this nx, which always sits in minus n delta plus n delta, but that nx also belongs to g. So that means minus n delta plus n delta is subset of g actually. Or if you choose any point in minus n delta plus n delta, you will easily verify that that point belongs to. So I will do it like this. Without creating any confusion here. Okay, I will first verify this part. This n delta minus n delta plus n delta is also subset of g. Okay, so let y belongs to minus n delta plus n delta. Then this y is equal to n times x, where x belongs to minus delta plus delta, which this nx, as x belongs to minus delta plus delta, so which is subset of g, because this minus delta plus delta is subset of g. So x belongs to g, which implies this belongs to g, as x belongs to g, you can see, as x belongs to g. So any y in minus n delta plus n delta is in g. So that means this is subset of g. This is subset of g. So which means that why you have chosen this x from R, but x belongs to g. So that means this g is subset of R, which implies g is equal to R. A contradiction. It's a contradiction because because it is a proper subgroup of R. A contradiction. Contradiction. So thus Lebesgue measure of G is always equal to 0. So any subgroup of R under addition is a null set. But the question is, can we construct any uncountable subgroup of R? So how do we do that? It's also proper